point two, talking about mathematical models. So there's ways to represent the data. And first model we're going to talk about is linear. So a linear model is just one that is fits the form for an equation for a line. So most likely y equals mx plus b. That's our equation for a line, or one of the equations for a line. So we might have this set of data that would be best represented by a line. So we might have these points of data, and they're best represented by some type of line that we can write this equation either in slope-intercept form, this is our slope, or maybe point-slope form, or standard form. But it's just a line that represents the data. So we have different types of functions. We have polynomials, like y equals or f of x equals x cubed plus 2x squared plus x to the fourth minus 3, something like that. Here, in most all polynomials, your domain is going to be from negative infinity to infinity. So there's domain. And then we have square root functions. So that's like f of x equals, let's say x to the half, something like that. Or I could represent it as square root x, any type of root there. So a more general form might be, say, y equals square root of a, some number, and then x out here. So this could be any type of root. So x could be any number. And then we can rewrite that kind of like as a to the 1 over x, right? Rational exponents. So there's a square root function. This one, sometimes our domain changes based on what type of root of it is. Square root, you can't have negatives in there. Cube root's fine, so any odd is fine. But even, we're going to have restrictions on that domain that we can put in there. Reciprocal function, so that's just talking about x to the negative n. So that we can rewrite that as x and to the, change that negative, bring it down to the bottom with n. Now it's positive, put a 1 on top. So anything like that, that's a reciprocal function. Here our domain, we can't have 0 on the bottom, right? So those are some restrictions to our domain. And then we have a rational function, f of x equals px over dx. It's a division function. And here again, this cannot equal 0. Cannot equal that function. So it's a function divided by a function. Right, so some function divided by another function. And this function can be 0 on bottom. So we use that truth or fact that can be 0 on bottom set equals 0 to help us find our domain. So you might have an example like something like this, f of x equals, so you have some polynomial function on top. Say x squared minus 1, you might have x plus 1 on bottom, something like that. So there you go. There's a rational function. You can simplify it, but okay, then we have our trig functions. Y equals, or f of x equals a plus, this is c plus a, whatever your trig function is, times, sometimes that b is inside and sometimes it's outside. If it's inside, minus d can be written like that, or it can be rewritten the same. That c could be at the end, and sometimes that b can be pulled out. So this is your phase shift in here, and then you're going to add a c at the end. So this could be sine, cosine, tangent, anything like that. So then we have exponential when our x is a exponent. So we have some base, some number for the base, but x keeps on changing, and then we maybe multiply that by some constant, right? That's an exponential. So our x is our inputs, what we plug into it. And we have a logarithm. Right, so sometimes we can take our log and multiply something by them. So it might be something like this. And then, but before we take the log, we might subtract. something from them. And then after that, I don't know what letter to put here. D, B, doesn't really matter. And then we might add something at the end, or you might see that backwards. C plus A log X minus D, something like that. Or you might see something out in front here. But you'll see something like that, right? Where you take X plus something or minus something, then you take the log, then you times it by a number, and then you add your constant at the very end. And logs, remember, logs kind of look like this. They either look like this, keep growing that way, or they might look like this, something like that. So there's a kind of our different functions that we kind of deal with, trig, exponential, logarithms, those kind of things, as well as these others. And so we'll use these, and we can write mathematical models for these. So sometimes the data is best represented by a rational function, sometimes best represented by reciprocal function or a root function or a polynomial. And there's different type of polynomials, right? There's x squared, there's x cubed, and it keeps on going and going and going. Or a data could be represented by a trig function or an exponential, right? Keeps on going. And these two, exponential and logarithms, are reciprocal. See how it looks like that? And then you flip it around, it looks like this. So our data can change based on what our data set is. We try to represent what it looks like in order to predict what might happen in the future or what might happen at a certain time.